In this video, we will do two things: define exponential functions that have a base other than e, the natural number, and we will also learn how to take the derivative and the antiderivative of exponential functions that have bases other than e. We begin with the definition of an exponential function with a base of a, which is going to be some positive real number not equal to 1. X would be any real number. Then we define a to the x as e to the natural log of a multiplied by x. And that definition will help us learn how to differentiate functions of that form. Next, we have a brief summary of properties of exponents. These are the same properties that you are familiar with from pre-calculus. And we move on to define a logarithmic function with a base of a. That base is not allowed to be equal to 1. And we define log base a of x as natural log, 1 over natural log of a multiplied by natural log of x. So in other words, it's the same thing as natural log of x divided by natural log of a. Similarly, with exponentials, we are followed by properties of logarithms, the same properties that we know from pre-calculus. Now we are going to learn how to differentiate and take the antiderivative of these functions. So here we have 4 different derivative rules. Number 1 is the derivative rule of how to take the derivative of a to the x. We get natural log of a multiplied by a to the x. And then number 2 is simply the chain rule version of that. So we use number 1 if all we have in the exponent of a is x. And in number 2, u is not just x. It would be some function of x. And we can see the chain rule showing up right there because we're multiplying by whatever the derivative of u was. Number 3 tells us how to take the derivative of log base a of x. Number 4 expands upon that. In case you do not only have x on the inside of your logarithm, then you have the chain rule showing up with taking the derivative of whatever was on the inside of that logarithmic function. So now let's start applying these rules. Example 1, we want to take the derivative of 2 to the x. We would be using this rule because we simply only have x in the exponent. And so y prime is equal to natural log of 2. In this case, a is 2. So I have natural log of 2, and then we will multiply that by 2 to the x. And that is our answer for the derivative. Number 2 is a little bit different. Our base is still 2, but this time we have something other than just x in the exponent. This time I will assign u to be 3x, since that's what we have in the exponent. I will take u prime, the derivative of u, which is 3. And I know I'm going to need that because we have this du dx coming from the chain rule. That's the same thing as u prime. So now I'm going to start filling out this version of the rule since we had something other than x in our exponent to see that y prime is equal to natural log of a, which is natural log of 2 in this case, multiplied by a to the u, so that's 2 to the 3x, and then we have to multiply by the derivative of u, which in this case was 3. I'm just going to move some things around here so this looks a little bit neater and write our final answer as 3 multiplied by natural log of 2 multiplied by 2 to the 3x. Moving on to example 3, we want to take the derivative of log of cosine x. In this case, please recall that when you see a log function written with no base, it is understood that the base of that logarithm is 10. So this is the same thing as log base 10 of cosine x. In this case, I'm going to be using rule 4. I can see that my base a is 10, and u, what we have on the inside of our logarithm, is cosine x. We're going to need u prime, which is the same thing as du dx. And we know that the derivative of cosine is negative sine x. So now we have everything that we need for us to begin filling out this derivative. So y prime is equal to 1 divided by natural log of a, which is natural log of 10. I also need to put u in that denominator. U is cosine x in this case. And then we need to multiply by du dx, which was a negative sine x. Now I'm going to clean this up a little bit because I know that a sine divided by a cosine is a tangent. And don't forget we have that minus sign in there. So we are left with negative tan x divided by natural log of 10. Now, moving on to example 4, we're again going to be using this version of the rule because it's not just x that we have on the inside of our logarithm. We can see that our base a is 3, and in this case, our u is the quotient of the square root of x divided by 2x plus 5. And in order to find u prime, we're going to need to use the quotient rule. So I'm going to go off to the side and identify f as the numerator and g as the denominator. We're going to take f prime and g prime, and then we're going to calculate f prime g minus g prime f all over g squared. That is us using the quotient rule. So f prime g leaves us with 1 over 2 root x multiplied by 2x plus 5. From that, we're going to subtract g prime f, which is 2 times the square root of x. And all of this is divided by g squared, which is 2x plus 5 squared. Now we have all of the pieces that we need for us to go back and write y prime. So we have 1 over natural log a, which is 1 over natural log of 3. Needs to be multiplied by u. So I'm multiplying by the square root of x divided by 2x plus 5. And then in the numerator, I will multiply by this du dx, which is all of this here. I'm just going to put this to the side. So I have 1 over 2 root x multiplied by 2x plus 5, subtract 2 root x. And in the denominator, we have 2x plus 5 all squared. Now I'm going to do some algebra to clean this up a little bit. Here, I have a fraction in the denominator. I'm dividing by a fraction, so that's the same as multiplying by the reciprocal. So essentially, this 2x plus 5 is going to be going to the numerator. The natural log of 3 and the square root of x will stay in the denominator. I'm going to go ahead and wrap that 2x plus 5 that's up there in parentheses. And let's see what else we are left with here. I do have some things that can cancel out because I do have 2x plus 5 squared in the denominator with the 2x plus 5 in the numerator. So I can cancel one of those out to be left with 1 over 2 root x multiplied by 2x plus 5 minus 2 root x. And in the denominator, we have a natural log of 3 multiplied by a root x multiplied by a 2x plus 5. Now we're going to look at how to take the antiderivative of exponential functions when our base is not equal to e. And we have this rule here, that the antiderivative of a to the x is the same thing as 1 over natural log a multiplied by a to the x, and we add on our constant of integration. I will mention that the chain rule version of that would be that the antiderivative of a to the u du is 1 over natural log of a multiplied by a to the u plus c. So we may need to look at a u substitution if what we have in our exponent of our integrand is not simply x, which is not the case in example 5, right? Example 5 looks a lot like this because it's just x in the exponent. So I'm just going to apply this rule directly to be left with 1 over natural log of 2 multiplied by 2 to the x, and I'll add on my constant of integration, c. Now example 6 is a little bit different because it's not just x in the exponent, it is x divided by 4. So I'm going to apply a u substitution and say that u is equal to x over 4. In that case, then my du, the derivative of u, would be 1/4 dx. We don't have a 1/4 in there, and so I'm going to multiply both sides of this equation by 4 to see that 4 du is equal to dx. This is a definite integral with limits on there, so I'm going to take some time to change those x limits into u limits. And I'm going to do that by plugging in the x values of -4 and 4 into u, which is equal to x divided by 4. So when x is equal to -4, u is equal to -1. And when x is equal to +4, u is equal to a +1. So now I can rewrite my integral with the new limits of -1 and 1. To begin my substitution, 3 to the x over 4 will be replaced by 3 to the u, and dx will be replaced by 4 du. And I can take that constant of 4 and pull it out in front of my integral. So I'm left with simply the integral of 3 to the u du, which integrates into, now I'm applying this version of the rule. So we are left with, don't forget that constant of 4 in the front, 1 over natural log of 3 multiplied by 3 to the u, which needs to be evaluated from -1 to 1, which is going to give us 4 over natural log of 3. I'm now applying the fundamental theorem of calculus. I will have 3 to the first power, which is simply 3 to the 1, minus 3 to the -1 power, which is simply 1/3. 3 minus 1/3 is 8 over 3. So we have 4 natural log 3, 4 divided by natural log 3 multiplied by 8/3 to give us a final answer of 32 divided by 3 natural log of 3. Now we have an area problem. We want to find the area bounded by these curves. I'm going to create a rough sketch of this. I would graph this function in your calculator if I were you, so that we can envision what this region looks like, because it is important that we know which function is on top and which function is on the bottom. Between 0 and pi, this function looks something like this. It hits the x-axis right here at pi. That is the point pi 0. So there's the vertical line of x is equal to pi. The vertical line of x is equal to 0 is simply the y-axis, and there is our curve. So to find this area, we would need to integrate from 0 to pi, since pi and 0 are the two regions. That says x equals 0, but should say x equal pi. Since pi and 0 are the two vertical lines that bound this region, so that's where I get my limits from. I want to integrate the function, which is 3 cosine x of multiplied by sine x, and then I stick a dx on the end of that. To go through this integration, we're going to need to use u substitution. U is going to be what is in our exponent, which leaves us conveniently with du is equal to a negative sine x dx, which is almost what we have left in the integral, except we don't have the negative, so I'm going to multiply both sides or divide by -1 to see that negative du is equal to sine x dx. I'm also going to take some time to change my limits, because I start off with limits of 0 and pi, but we have that u is equal to cosine x. So when x is equal to 0, u is equal to 1, because cosine of 0 is 1. And when x is equal to pi, u is equal to -1, since cosine of pi is -1. So now I can rewrite my integral as the integral from 1 to -1. Make sure that your lower limit, which was originally 0 and turned into 1, is still the lower limit. And the upper limit, which was originally pi and turned into -1, is still the upper limit. And now we're just left with a 3 to the u from the 3 to the cosine x. And then for sine x dx, we're substituting in a negative du. I'll stick that negative in front of the integral, and I'll stick the du at the back. So 3 to the u du integrates into, we still have that minus sign, 1 over natural log of 3 multiplied by 3 to the u, which needs to be evaluated from 1 to -1. So I'll go ahead and keep my constant of -1 over natural log of 3. I'm going to apply the fundamental theorem of calculus, which tells me to plug in my upper limit, subtract, and then plug in my lower limit. When I plug in my lower limit, we have a 3 to the 1, which is simply a 3. It might be easier to rewrite the 3 to the negative 1 as a 1/3, and 1/3 minus 3 is a negative 8/3. And then when we multiply, the two negatives will cancel and leave us with a positive 8 divided by 3 with a natural log 3 in the denominator.